So last week, I'm going to do a very brief. So previously on the cisst multitask topic, we introduced the cisst multitask component. I think the key elements to remember is the ability to have a provided interface, which is a list of commands and also events that can be used for like an upper layer application. Built-in mechanisms to deal with thread safety, including state tables and commands for queues. And the fact that components can be either kind of the client producer side or on the server producer side or on the client consumer side. And on the client side, they have a required interface for all the features that they need to be able to function. We talked a little bit about the threading in general. So in general, cisst multitask is very good at providing multi-threaded, safe, multi-threaded, and efficient. The next thing we talked about very briefly was CRTK. CRTK is once you have all these components, you need to make sure the interfaces are somewhat standardized. And the standardization here is based on the command names and for both the operating state, which is the robot enabled, disabled, is it home, is it ready to be used, and the motion commands. So the motion commands we have here short tables. You can see that there is from the robot on the right side to the application on the left side. You see the arrows measured is what the sensors are going to tell you. Set point is what the low-level controller is doing, and goal is going to be the high-level controller. And then the other way around, you can send a servo, basically control the goal for the low-level controller. And then we have move and interpolate, which are not as well defined in the CRTK convention. So CRTK is still a standard in that needs to be defined in some areas. This table is a bit of a summary of this. So for the feedback, we have the set point, low-level controller, goal, high level, measured, every time. Measured is a sensor feedback. We have a convention for measured 1, measured 2, measure 3 for redundant sensors. That's the case of the DPRK with potentiometers. And then the other way around, you can servo to send a direct command to the low-level controller, or move, which is more like move from point A to point B and assume there's a trajectory generator behind the scene. And then we have this suffix, which is the suffix in which you're moving. So _J, _C for joint Cartesian, and P for position, R relative. So if you put that all together, a servo JF is a direct command to the low-level controller to apply F, a torque, a force. J is for joint. So you're applying joint torques. Set point CP is what you're getting from the robot. It's a feedback. And it's where the robot is trying to do is Cartesian position. It's a very brief overview of CRTK. The reason I'm doing this is because these keywords and function name will show up later in the presentation. This thing that presentation that we had last week that Peter introduced, we talked about component-based and mentioned that both ROS and cisst are component-based in some ways. One of the decisions in cisst was to use multi-threaded in a single process. But we did know, so that's the architecture you have here. The black box is a single process, and each, the client and the server, for example, 2 different components are working in different threads with thread-safe mechanisms to talk between each other. But what happens if you want to create something over the network? And from the beginning, we had the idea of having this kind of a automatic generation of a client bridge that would figure out what to get the information back and forth from the client to the server through 2 bridge components. And these components are also cisst-based, so they are running in their own threads and getting data back and forth between the 2, doing serialization. You need to serialize the data, deserialize the data between the 2 different processes. So we looked at different implementation possible, and one of our PhD student, Min Yang, who then went to work at Siemens, I think, and is now working at Intuitive Surgical, we decided at the time to use ICE from CRTK to do the middleware and generate all these bridges automatically and connect them automatically remotely. Turned out the implementation got a little complex and hard to maintain. So this code is not maintained anymore, and we're looking at something a little bit leaner. In between, Peter implemented something that is purely UDP based, between two cis components that is fairly lean, not fully automated, but usable. And then as we were working on ROS and cisst and the cisst and the DVRK, ROS popped up on the radar, and we started to think about putting ROS as a middleware. There are other options like OpenIGT-Link and whatever we want after that. I'll mention at least OpenIGT-Link. Obviously, between the two, you're going to have to do data conversion. You're going to have to make sure the models are the same. The execution model is the same. Why use ROS? Mostly because it's widely used in robotics. It can interface with many other packages. So you can have a ROS joystick. You can have the data collection with a ROS bag. You can have 3D visualization with RViz. You can have dynamic simulation with Gazebo. You can have all these packages that are available, and it makes sense to start interfacing with ROS. The cons from a perspective, and when we start to use ROS, you have to use Linux, Ubuntu Linux. We had, and we still have, some hardware dependencies on Windows, so it was not necessarily a slam dunk to go to ROS 1. The other cons, kind of more recent, is ROS 1 is slowly being deprecated and migrating to ROS 2, though it's kind of like the Python to Python 3 migration. It's impeding, but in the next 10 years. So we kind of have to be aware of that migration, but it's not completely clear when it will fully happen for the community. The other thing that is cool here, and initially you can see we had this little line going between two cisst-based application processes. But now, because ROS has its own environment of application and nodes we can reuse, this ROS node can be used with just the server side of cisst. We don't have to have the client side. We could also have just the client side and then ROS on the other side. So it's a level of flexibility that we didn't really have in mind initially, but is very, very useful. What is different between ROS and cisst? There are some commonality. The first one is we came up with the language description for a payload. ROS is coming with the MSG file. I don't know if you're familiar with ROS, but it's a little file that says I have this object of this type, let's say a float, and it's called it scale, and then I have a frame, and I'm going to call it position or something. And then the message generator will parse these files and generate C++ code for all the function you need to do on this object, mostly serialization and deserialization. For cisst, we actually came up with the same idea about the same time, and we call it cisst data generator. It is completely proprietary, and it's my code. But it's been introduced, and that's the last point on the list, it's been introduced a little bit late in the cisst libraries. So some data is still using the old system, but we're really trying to migrate everything. Last note, you're going to start seeing the convention PRM in some names of classes. It's for everything that comes from the library cisst parameter types, and that's where we standardize the payloads. The reason for that is we want to have standardized API. You cannot decide to send a frame as a vector and quaternion, or frame and rotation matrix. We need to agree on a standard payload for messaging. For computing, you do whatever you want. You can convert back and forth, but for messaging, you need to standardize. The other thing that is slightly different, but finally not that different between ROS and cisst, is what mechanisms do you have to communicate between your two components? And here I'm going to focus on ROS, essentially ROS publishers and subscribers. When we looked at the cisst multitask component, we had data that was available for higher level application that we put in a state table, and we provide a read command to read from that state table. And in the cisst model, what happened is the consumer, the client, decides when, so that the consumer here who triggers when to read. In ROS, you don't really have this mechanism unless you want to use services, which have all kind of latency issues. So in ROS, what happened is the server will continuously publish data, let's say joint position. And so here the trigger is done by the producer. That's really the main difference. The other command that we have in cisst, you can have a void command. So a void command is basically someone telling you to do something, let's say stop. And that's fairly simple. It's triggered by the consumer. It's going to stop the robot. And in ROS, it's a subscriber with a message. You have the same thing with a payload. So write, so let's say like go to, and then you give a position. Same model, it works fine. And also in cisst, we have in the server the ability to send an event. Something happened. Let's say I had an emergency stop. We can do the same thing now. And what happened is, as a ROS topic, is I'm publishing something. So that's, again, triggered by the producer. And you can have the same thing with an event. Let's say my scale has changed to 0.5, and then you publish the same thing. So the biggest decision we had was what to do with the cisst read command that are usually triggered by the consumer, not by the producer. It turns out that in cisst, most of these read commands are data that is accessed, that is from a state table that is refreshed periodically. So it kind of makes sense for us to have a bridge reading from that continuously and continuously publishing at a given rate. And that's the user's task to define at which rate do they want to publish that. That's kind of the biggest difference in the execution model between cisst and ROS, and that's where people need to be a bit aware when they use the code. What's happening in practice? So like I describe all this execution model and data conversion. I'm going to explain now a little bit what happens. Let's say you have a cisst component and it has two values, value 1 and value 2, and two functions. One is to allow you to read value 1 and one to write value 2. And in the run method, all it does is automatically assign value 2 to value 1. It's a dummy component. All it does is cache the value. What does the bridge have to do? The bridge has to be able to, when it receives, so the ROS node here will have now a subscriber to val1 to be able to know what value 1 is, and it has to be able to send a value to val2. That's on the right side in the pinkish node. And what I'm doing here, I'm going to say I'm going to get the value, update the value 2 as being val1 plus 1, and then publish it back. The code here is basically going to do in the run loop, there's going to be a continuously running loop that is going to continuously read what is in the cisst component value 1, convert it to ROS. So we talked about conversion. You need to be able to convert back and forth, and then publish it. So now I have continuously publishing value 1. Whoever has updated it, ROS node will have it accessible through the subscriber to val1. When I publish to val2 from the ROS node, what gets triggered is the callback, the val2 callback here. And here again, we have to convert the data. So now we're going to convert from ROS to cisst. And then I'm going to call the write val2 command that is available in my cisst component on the left side. All of that is completely thread safe. These cisst component and ROS bridge run in two different threads in the same process, and the ROS node is yet in a different thread. I'm going to go a little bit more details about how it works. And Peter mentioned that was maybe a little too boring for the attendants, so I'm going to go really fast on this one. So this is how do you populate a server bridge for cisst-ROS, and how do you populate a client bridge for cisst-ROS. Here, if your server has a provided interface, the bridge will have a required interface, so it can connect to it. And it can convert the read command, the events, and the write command. I'm just going to go really fast on these 3 bullets. On the other side, your bridge, because it will connect to a required interface, now creates a provided interface. It is confusing. I actually got confused when writing these slides, and I had to go back to the code. So it makes sense. Don't worry too much about the language here. I'm putting it mostly in the slides so people can refer to it later in the future. Yeah. So in general, you have to use the derived from the MTS ROS bridge and use one of these 6 methods to do everything we're doing. Some of the students here have struggled to do that or have been looking at example and are like, this is scary and I don't want to do it. I want to add a few more technical points about the cisst-ROS bridge, because some might think it's just, why would I use a cisst-ROS bridge when I can write 3 lines of C++ code that will create a ROS publisher, and I don't care about this component-based approach. It's a pain in the neck. So the few things that I want to mention is, first of all, the conversion. We have a ton of conversion method between cisst and ROS, so you don't have to redefine conversion method for all of these if you use the component. The second thing is we took some time to be very careful about timestamping. Cisst multitask payloads, most of the payloads have timestamp. Most ROS data types also have timestamps. If you're not cautious about it, you're going to send a bunch of zeros or values that are a little bit old. So what we do now is we take into account the age in the process of cisst and subtract it from the ROS now and publish this way. So your data is fairly well timestamped, as well as you can on the code. And it's done automatically for you, so you don't have to worry about it. The other thing that we do, and that's a little more controversial, more difficult to do, cisst multitask has a valid flag for data. Let's say, for example, you're tracking a Polaris active tool or a passive tool. At one point, the tool is not visible. You need to know the tool is not visible. So within cisst, there's a flag that says there is some data, but it's not valid. The tool is not visible. ROS does not have the equivalent. So what we decided to do is, in this continuous stream of data that we publish, we stop publishing. That means it's the responsibility of the end user to look at the data and say, I'm expecting some data at 50 Hertz. I don't see it. That means the instrument is not visible anymore. We have some wrappers in cisst-Python that in a ROS Python client that actually handle that for you. The last thing I want to mention, I talked about services only right now. We do support services to an extent. There is a quick example that's used in the DVRK to say what is the forward kinematic up to joint end. So you send a vector of joint value, it returns you the frame corresponding to that nth frame. It's useful if you want to do your own 3D rendering, for example, link by link. You're going to query link 1, link 2, link 3, link 4, etc. We also support broadcast to TF2, but not the other way around. And the last bullet is we do not support ROS param at all. We did not have an equivalent in cisst, but every time I see it, I feel like it's very useful. So that could be also in the list of to-do or student project. That could be a really good project to tackle. It would be really, really useful. When you get to the actual code, it looks something that ugly. You describe what you're wrapping and what direction. You need to use C++ templated code to say what type goes to where, from what to what. And then you have the interface name, the name of the command in cisst, and the ROS topic. And that's where I had my special effect that ROS decided to deflate. So really, and no, I don't expect all users, nor myself actually, to remember all the method in the NTS ROS bridge. I know C++ templates can be scary, so I'm not going to expect everyone. And also, we end up having to recreate a ROS bridge that looks almost the same when you switch from the Polaris to the Atraxis, from the GR3 force sensor to another force sensor. So you end up having a lot of repetition. So the reason on what I gave you that is because this presentation is because I want people to understand the limitation of the ROS bridge. And I also want to show that there's a lot of implementation there. So if you try to redo it yourself, you're likely going to make mistakes that we have made and took us a lot of time to iron out. I think Adnan is in the audience right now. He remembers the DVRK performance of the cisst-ROS bridge 5 or 6 years ago. That was abysmal. And it is now very usable. So you're going to likely run into the same thing. So what now? Right now, well, we talked about CRTK, and I think now I'd start to use it in the ROS bridge. Why CRTK? Well, if we have a component with a proper CRTK interface that only use CRTK command name and corresponding payload, that's a pre-existing condition. cisst multitask has the ability to automatically scan all the interfaces of a component and the name of the commands. If we know these, then we can automatically populate the bridge. So if we have all of that, and if only if, then we can create automatically that bridge. And that makes the code look like this. So you create CRTK bridge, and you say bridge interface provided. You need to provide the name of the component you want to bridge, the name of the interface. The ROS period is to say at how quickly do you want to push all this bridge command, and the TF period is usually a different rate. TF tend to not like anything about 50 Hertz, so you do that. And what this code does is create the cisst-ROS bridge, create the CRTK interface required, or as many CRTK required interface for as many components as you're bridging, and then publish it to ROS. And this class, by the way, can be expanded. You can get access to the internal data structures and expand it for non-CRTK bridges. Icing on the cake, cisst multitask can be using dynamic loading. So you can have a cisst-ROS-CRTK bridge and say, hey, by the way, I want to interface. This is a list of interface I want to wrap. This is a component name. Let's say the Sensible HD. Which interface do I want? The Omni. And I can create whatever namespace I want. Clearly here I was playing with it when I was developing the code. So you can call it Omni1, Omni2, left, right, whatever. But you can also select a subset of commands. If you don't want to publish everything because that's too much, you can select a subset. And you can control the publish period and the TF period using a config file. Zero code, just a JSON file. A few other things about the CRTK bridge. One that is actually pretty crucial and Adnan will appreciate. If you do a single loop running, let's say at 100 Hertz, everything that's going to happen and go through your bridge is going to be gated at that rate. There are things you don't want to gate. You want them to be synchronous, not asynchronous. So for example, if you have all events coming from your component, you want these events to be published as quickly as possible to ROS. So for that, the CRTK bridge creates a separate thread using the base class MTS ROS bridge to run as fast as it can. For all commands coming from ROS, now the other way around. Let's say I tell the robot to stop. I don't want to gate that command and wait to dequeue it. So there's another thread here that is just waiting for command from ROS and does all the spin and triggers all the callback, and it's going to send the command as quickly as possible to your sys components. There's another one for TF because of this different rate. And finally, each ROS bridge that you ask to publish, let's say, for example, your very low level IO at 1 kilohertz, but you can also publish a high level goal at 50 hertz. So we're going to have a thread for each of these. This is managed automatically for you. You don't have to worry about it. Last thing to note is all these threads are running in the background, but we're also publishing the statistics about these threads, like what is the actual periodicity they're running at, what is their load, basically the ratio of time being used to get the data, convert it, and then send it to ROS. So all of that gives you a pretty tight control about what the system is doing. Here are some links. All of these links have readmes. The main things are the cisst-ROS, there's a main readme for everything describing cisst-ROS and cisst-ROS-CRTK, the repository for the two classes, and a couple of examples. The first one is for the Sensible Phantom. That's the simplest example. It's literally wrap that interface, publish. And the other one is the DVRK, which is much more complex because we have about 4 or 5 different classes that are wrapped. There's derived classes, different types of topic, depending on the arms, and topics that really don't fit into the CRTK. So they are their own classes. But if you want to tweak on top of CRTK, that's very useful. So now all is good. You have a CRTK device. Here I'm showing a screenshot of the Falcon, which is a small little haptic devices. So you can see the top are just the name of buttons. Device state, measured GS is moving, measured CF, measured CP, measured CV. You can see here all the CRTK commands. So now you can start working on your own application in the ROS space and write your code. Oh, sorry. I didn't really rehearse my presentation, so I should have prepared for this one. What is CRTK compatible at that point? Obviously, the DVRK. We use that as the driving application for everything. But I also use the Sensible Omni because I have one on my desk, the Falcon. I also have one on my desk. Force dimension in general, as well as NDI tracker, the Atraxis, the ATI force sensor, the OptoForce. So all of that is already supported. I believe AMBF is also completely CRTK compatible. Yeah, this slide is a mess because it says CRTK ROS and I have things not related to ROS. Sorry about this one. I'm going to skip on this one. Once you have a device with a CRTK application, you CRTK ROS interface, you have to start writing your own subscribers and publishers in whatever language you want to write your application in. And we have found at Johns Hopkins that many undergrad students, high school students visiting have a hard time understanding what's happening there. And sometimes it's not the goal. We don't want to waste time re-implementing code that someone else has already implemented 10 times. And we really want to focus on the application level. So the main goal is to simplify the application development. ideally hiding ROS layer as much as possible. Using conversion data types that make more sense. ROS sends you a struct. So a vector is X, Y, and Z. There's no available algebra on it. So the idea is to convert that under the hood to something that now you can do multiplication of frame by vectors. You can do all these kind of things. The other thing is also to hide high-level features. Like if you have a weight on an event, we can probably implement that instead of having every user running a while loop waiting for something to change. So all of that needs to be done. Then we started to talk about a very specific example, which is the ROS Python client API. So now let's say you want to write your application in Python and you talk to a CRTK compatible device. Let's say the DVRK or the Omni or whatever. So the first thing we did is to hide all the ROS-Py publishers, subscribers, and everything. Then we decided to use the convenient data type, and basically we use PyKDL, which has frames, vectors, rotation matrix, conversion back and forth with axis angle rotation, quaternion, all of that is built in, so you don't have much to do. For everything that is dynamic size, for joints, twist Jacobian, we use NumPy, which is a standard in Python.
Sure.
And then ultimately, we also end up using the Python threads for everything that is blocking, non-blocking. So you can create a thing that says, wait with a given timeout, and you don't have to worry about Python threading behind the scene, which is a bit of a nightmare to deal with if you're a novice programmer. The first set of decisions for the Python client API. The second one is something that we learn painfully on the DVRK, is if your Python client subscribes to absolutely everything your device provides on ROS, what ROS will do is continuously serialize, send, deserialize, and trigger callbacks on your code for for objects that you might not even need. So for the DVRK, for example, if you're trying to do something in joint space, and the DVRK sends you the Jacobians, the Cartesian position, all of that, your client will receive absolutely everything, and that will bog down your PC to a point where it can become hard to use. So we decided very early on, it is interesting when you write your code to say, hey, I'm interested in this feature, and that feature only. So we can select which subset of features. It also allows you to adapt your client to what features the main device has. Let's say if you're talking to a Polaris, you're going to have a measured Cartesian position, but you cannot send the Polaris a command to say, move to that position. It's a passive system. Whereas if it's a robot, you can have the measured position, but you can also tell it to go to that position. So that allows us to really tailor the client to the server that you have. So I want to provide a quick example of what I'm talking about tailoring. And this is snippets of code. It's not all tied together, but what we do is we provide this little class called CRTK util, which is in Python. And for this class, you need to say, this is the ROS namespace where things are going to be coming. Let's say my DVRK/PSM1 is one of my ARM. I'm going to subscribe to all these ROS topics, and that's going to be my interface to my ARM. And for this ARM, I'm interested in getting the operating state. I want to know the setpoint CP, and I want to be able to send a move command. So I'm going to add all these features to my class. Once this is done, in my class, I can do self.setpointCP, and that tells me the Cartesian position set point from the robot. What's happening behind the scene here is really when you call that function, your client has cached a value that it has received through a subscriber that the robot has sent periodically. So all of this is completely hidden. So it looks like you're just getting the position of the robot. So the code is fairly simple. The .p.m is position and rotation matrix in PyKDL. I'm not super fond of the convention, but this is what it is. It works very well. So, you know, beggars can be choosers. And then on the other hand, once you get the set point, you can start manipulating. Let's say you can add the line underneath here. You can add a little bit of a motion, and then you can make it move. And the way the CRTK client, it gives you a handle. So like, hey, you asked me to move. Let's get a handle on it. And I'm going to wait until that move is completed. That wait, by the way, has also an optional timeout. I can say, hey, I'm going to wait, but not too long, because I'm not really trusting you that you're going to be able to do it. Okay. And based on that, the handle is going to give you another result. Okay. Underneath the last line, you have a more compact writing of that. You can say, just move and wait. what's happening behind the scene when I do the add move CP? Well, internally, there's this move CP command that has the data conversion. If you send the goal here is a PyKDL, I'm converting this PyKDL to a message. I'm creating a special wait handle, and then I'm publishing to ROS. This is the code that you don't want to see, that you will never see. This is what the code is doing behind it. When you do an add move CP, there's a quick check to make sure you haven't done it already, the first 2 lines here. And then you create the publisher here that says, I'm going to publish to this move CP there. And when we play this little trick here, which is you can now create a link in Python in your class. So when you call, see this little .move CP here, it really calls the utility method __ move CP. It's a way to kind of populate the interface dynamically in Python. It's cute for people who do Python. We have the exact same thing in MATLAB. So exact same thing. You can add move CP, you can add set point CP, and it's all over ROS. So if for people who are interested in MATLAB for different reasons, because they're familiar with it, because they have a deep learning algorithm in MATLAB, because they want to run on Windows or they want to run on Mac OS, which is one of the few cases where you can use ROS over on these OSs because it's Java-based stack, then you can run this on MATLAB. And you can do funky things like getting the translation is the 4th column, first 2 elements, to change your X and Y translation and do all this nice little syntax. And you get the same thing. You can do the .wait, and everything is equivalent. But internally, it obviously uses different data type conversions. A frame is a 4x4 matrix in MATLAB. It's just easier to multiply. And the threading is different, but this is a whole Eden with tons of code that we had to write and debug in the CRTK MATLAB client. There's a lot of documentation for these, and I've been, in time of COVID, I had a bit more time and less distraction, so I had a lot more READMEs. So all of these repositories come with READMEs. Feel free to use and go read, and they are in the presentation, so people will be able to find these links later. So now, cisst-ROS-CRTK, cisst-ROS-2 CRTK. I've described ROS1, and I mentioned that ROS2 was coming, and ROS1 was going to die at one point. So what would it take to do that? What needs to be updated? And I'm going to take here an example of this big slide that I had initially for the DVRK. In the DVRK, we have in gray here a lot of Qt widgets. We have a ton of file parsing, component logic, multi-threading, homing, and everything in the blue component. That stays exactly the same. There's nothing to do. The part that changes a lot is how does the CRTK ROS bridge works? And now it's called the cisst-ROS-2 CRTK bridge. And that code is my code. As long as I provide it, you guys have nothing to do about it. The little piece of code that I have to change is the main, where you say, hey, I'm going to use a cisst-ROS-2 bridge, not the cisst-ROS bridge. And there's a bit of how do you create your ROS node is different. That's not my fault. That's ROS2. So you can blame them if you want. So mostly it's the cisst-ROS bridge and the ROS2 bridge. And I rewrote it. Took me about 2 weeks, about a week full time. And you can see here a screenshot of the DVRK running with cisst-ROS-2. It's not very easy to see because it's the same GUI, same window, same everything. But I do a little zoom up on that command. And now you can do ROS2, topic, echo, whatever. It just works. And that means in about 10 lines of code, I can now provide a ROS2 wrapper for all the devices that I mentioned earlier. The Omni, the force sensors, the Atraxis, the Polaris, whatever. And that's where the component base pays off. I mentioned that it works. I still have a few things to do. One thing is the CRTK Python and MATLAB clients are not implemented, which means you have a ROS2 node, but there's not much you can do with it. So for users, I think it's important. For me, it's pretty vital because all this DVRK unit testing that I do, a lot of the DVRK unit testing that I do is through Python script that runs over ROS. So I need to be able to do that. So it will give me a good way of testing both the ROS2 bridge and the DVRK itself. The build process right now is not documented. For people used to type Catkin build, good luck. Catkin is dead. It used to be renamed to something called Ament, and now it's called Colcon. And I wouldn't be surprised if the next release of ROS2, it has a new name. But for now, it's called Colcon, and I need to document it. I'd like to use VCS tool for distributing all the different repositories we use. We use WS tool right now, but it needs to be ported to VCS tool. And there's another thing that is kind of annoying with Colcon. It's not really good at building non-ROS packages, and we have all our core packages are not ROS. So we need to figure out a way to distribute that. I've done some work on creating Debian packages, so like binary packages. So you have to just say apt-get install cisst, and it installs it. I don't know how reliable that binary distribution is. So the alternate solution is to type make install, and then you have that install on your machine. It's not as nice as the old Catkin build, but it should work. The other thing is ROS comes with a whole bunch of other things, RD file, launch files. I have no clue how these are going to be impacted by ROS2. If there are users who are interested in helping with porting the DVRK to ROS2, raise your hand or reach out to me, and I'll work on that. And then ultimately, I stage all this code in my own repositories. I kept the links in here for people if they want to look. And for people who are going to refer to this slide in a few months, when we move the repository, there's a new destination organization where these things ultimately will be going. Talked about ROS and ROS2. I want to mention quickly OpenIGT Link middleware. So it's the same logic. You have an interface, it's CRTK compatible. Can you have an application or a bridge that will go through that interface and make it available to a different middleware? So why OpenIGT Link? Mostly for people who work with Slicer and image-guided system. It is a much simpler and less featured middleware than ROS or ROS2, but it does run on Windows, Linux, and macOS, which has advantages. So recently I had to help a student at Queen's University, who I think is in the attendance, to interface a sensible Omni with Slicer, and we were able to redo that on Windows with the code base that we have. There are some links here, and I'm going to provide a very quick example of how it works. So if you're familiar with a cis multitask, you create your bridge. That's the first line. You set the port, that's a UDP port on which you want to communicate, and you add the component. And then later on, the Omni can have multiple Omnis on the same component. So that's why you have a loop here. You can have a left Omni, right Omni in theory. So here what I'm doing is say, hey, bridge the interface provided from that component, left Omni, and the name is the name you want to see in OpenIGT Link. And that's it. These are really the 4 or 5 lines of code. And from there on, you can receive and send commands over OpenIGT Link. Same thing that we did similarly to ROS2. What's the time? Hey, I'm on time. One last thing. That's a pet project that we had for a while, and I've heard on the DVRK community, the question is, do you provide a MoveIt interface? So MoveIt is the motion planner, the de facto motion planning tool that comes with ROS. It does collision avoidance. It uses the RDIF for the description of the model and the CAD models. And then once it has found a trajectory, it has to interface with the robot using a predefined set of messages. And I think it's called joint trajectory. I can't remember exactly what it is. The ROS topics that the DVRK publishes are not compatible with the ROS topics that MoveIt expects. So it doesn't work. We could try to emulate this, but emulating these is a pain in the neck. They have all kind of little condition, timing, they send updates, they send all of that. The way it's usually interfaced with is a little class called ROS control, a part of the library called ROS control. And ROS control is a library that will do the trajectory generation, send the updates and everything. And all it needs is what it call a hardware interface. How do I talk to the robot? And the way it talks to the robot says like, hey, I need to know what is your current joint position, joint velocity. and I need to send you a set point. This is exactly what we have standardized in CRTK. So my idea is to say, well, I can use it in ROS, purely in ROS. So I'm using, let's say, the first line example here is I have my ROS CRTK device. Could be the your robot, could be the Omni, could be anything I want. I'm going to subscribe to these few topics that I need, inject that as an abstract layer of robot hardware for ROS control. And now ROS control provides me for free the interface that MoveIt wants. It's a little clunky because you go over ROS to talk to that thing goes over ROS, the ROS control, and ROS control goes over ROS to talk to the DBIK. But I might as well implement that directly as a required interface in ROS. I have some prototypes for that, and it kind of works. MoveIt requires a lot of extra configuration files around it, so it is hard to distribute and make available for the community. Again, that's a project that if anyone in the community, in the lab is interested in, let me know. I think for the DBIK, it doesn't make much sense because collision avoidance for an RCM type robot, you don't get collisions in the scene. The scene is just your shaft. It's not like a serial robot, like a UR5 or a KUKA or something like that. So it's a little bit harder to justify. In my mind, it's harder to justify trying to use MoveIt with the DBIK. Another advantage of using the ROS control, and I think that's where it pays off, not just for MoveIt. In the future, if the ROS control community start expanding to other trajectory generator, other controllers, then we might be able to piggyback on that because we already have the hardware layer. So that makes, suddenly we get access to all the ROS control controllers. That could be useful. And it looks like they might be interested in moving to be using Cartesian trajectories directly in ROS control. That's another thing that we could piggyback on if needed. So that's it for me. And I think Peter wanted to conclude with the last slide.
Yeah, I added this slide. Like, okay, now that we've gone through all of this, given that some of this stuff was started almost 20 years ago, what's the value today of all of this? And I think that, one is that if you look at the cisst multitask and OS abstraction and all the different libraries, it's still a good package for portable, that is portable to between different operating systems, multi-threaded, real-time code. And I put real-time perhaps in quotes. It really depends on your operating system. Mm-hmm. It'll run, efficiently on Windows, but it won't be hard real-time, for example. And so it's not the only package out there for that, but it's still, I think, a good one for that. The other aspects are really what we got into today, which is there's this middleware agnostic component-based interfaces. Where you basically say, okay, what is the kind of services that this thing provides, my component provides, and then what are its dependencies? And it's done really only in just straight, C++ code and strings and things like that. So it's very self-describing. And then we've also worked a bit on standardization, more than just standardizing, okay, ROS, choosing, let's say ROS middleware is one, or choosing ICE or choosing UDP. Those are all making a choice, but then within that is like, okay, well, what do you actually call your message or your topic or whatever it is, and then what is the payload like? And so there's not a lot of standardization in that. Even in ROS, you have these standard message types that are maybe sort of used most of the time, but then there's different variations, and so we're trying to really be a little bit more specific on the standardization. And then if you look at those last two bullets that I just mentioned, the final thing is that you can take all of that together and, as Anton showed, basically generate middleware bridges. So you can very quickly, if you don't have to basically invest through all your work in ROS1 and then ROS1 gets basically discontinued, you need to switch to ROS2, you don't have to start over. In fact, you have to do very little to be able to automatically generate interfaces with this new middleware, ROS2, OpenIGT-Link, whatever, as well as these interfaces through Python and MATLAB that were also described. Mm-hmm. So I see that as really the value of this infrastructure today is really providing some value in the real time, but then in a way of essentially describing your code in a more abstract manner, and then being able to plug it together using one of these supported middlewares. Yeah, that was all I wanted to add. So I think we're done for today.